Assalamualaikum and good day, student. Today we will look into another section in multi-phase system. We will look into gas liquid in equilibrium. Okay, and particularly we look into single condensable component concept. Okay, what does it mean by gas liquid in equilibrium? Okay, gas liquid equilibrium is like this. Let's say you have a closed container which initially only contain dry air. Okay, and this system is initially at 75 degrees C and pressure at 700 millimeter mercury or 1 atm. And then you introduce water to the system. So this is your water. Okay, water as a water liquid into this closed container. Initially it was all air, and then you put water. Okay, H2O. Okay, as time goes by, water will start to evaporate. And water vapor will be in the gas phase. Okay, initially it's just air, but when we start to introduce water, and as the time goes, the gas phase will be filled with water vapor that evaporates. Okay, so when there's no transfer of water vapor into gas phase anymore, so that is the condition when we call gas liquid equilibrium. When there's no transfer of water vapor into the gas phase anymore, where gas phase is already saturated with the water vapor, that is a condition where we call gas liquid in equilibrium. Okay? When gas and liquid phase in equilibrium, there will be no more transfer of water vapor into gas phase, and the gas phase is saturated with water vapor. So that is what we call gas liquid equilibrium. Okay? Single condensable component is, okay, we have air and water, H2O vapor now. So when we talk about single condensable component, so if we have in gas phase air, dry air, and also water vapor, so which one, if the temperature is being reduced, which one will condensate? If we reduce the temperature, which one will condensate? So the one that will become condensate is water. So in this system now, at gas liquid equilibrium, single condensable component, if you have air and water, when temperature is being reduced, so this water vapor will become condensate. That is what we call single condensable component. Okay. Important thing that we have to understand in this concept is the Raoult's law, where Raoult's law is given by this: partial pressure of the component equivalent to the mole fraction of that component in the gas phase times by the absolute pressure of the system equivalent to vapor pressure of that component at time T. At a temperature T. So Raoult's law say, if a gas at the temperature T and P contains a saturated vapor, if a gas at the temperature T and P contains saturated vapor, in our case now saturated vapor is water vapor, whose mole fraction is Yi, okay? And if this vapor is the only species that would condense, if the temperature slightly lowered, then the partial pressure of the vapor in the gas is equal to the pure component. This partial pressure will be equal to the vapor pressure of that component at system temperature. Okay? So this is what being emphasized by Raoult's law. If you have this partial pressure at gas-liquid equilibrium will equal to this. This will equal to this. Right? So the partial pressure we known as partial pressure is equal to mole fraction of that component. Partial pressure of a component is equal to this is single condensable component is equal to mole fraction of the single condensable times by the pressure of the gas or the pressure of the system when in equilibrium is equal to vapor pressure of that component at temperature at the system temperature. That is what is being emphasized by Raoult's law. This is Raoult's law. Raoult's law, single condensable species. Okay, so in your textbook it is equation in your textbook equation 6.3-1. So we have to understand this concept. The vapor pressure will help you to determine what will be the mole fraction of the at equilibrium. When it is in equilibrium, when gas liquid in equilibrium, Raoult's law equation here will help us to find the mole fraction. Will help us to find the mole fraction of the single condensable in gas phase by knowing what is the vapor pressure of that single condensable component at the temperature T. So this is the concept that we need to understand. This concept can be applied when we have gas and liquid in equilibrium.